Hi, welcome back. This is lecture 16 of the CS Theory Toolkit course. This lecture is about expander graphs. So, expander graphs, what are they? Well, in fact, we mentioned them a little bit in the last lecture. These are essentially graphs that are highly connected, yet which have not too many edges. So they have lots of applications in computer science theory. They're almost ubiquitous. This resource I've mentioned here is a wonderful survey about them. It tells you most everything you need to know. I should also mention that when I was a graduate student, I found expander graphs really mysterious and I didn't feel like I understood them very well. So hopefully I'll get the chance to demystify them for you a little bit. Okay, so there is not one precise universal definition of expander graphs. It's a little bit more of a concept. So we can make precise definitions, but let's start out a little bit more at a high level. So roughly speaking, what are expander graphs? So an expander generally means a graph which have three properties. First, the graph should be highly connected. Okay, so it shouldn't be a disconnected graph, and it shouldn't, have some vertices that are, just dangling off with only one connection to the rest of the graph. Every set of vertices should be well connected to all the other vertices in some sense. We'll be more precise shortly. The second property of an expander graph is that it's sparse, meaning not too many edges. So you can sort of get the ultimate superconnected graph if you take the complete graph, which has on the order of n squared vertices in an n vertex graph. But when people talk about expander graphs, they usually insist that the graphs be sparse. Most ideally, they should have only a linear number of edges, big O of n edges. Okay, so this is a bit in tension with the idea that all the vertices are well connected to each other. It's in tension with having not too many edges. Okay, so these are two key properties of expanders, but there's one more property. Typically, when people talk about expanders, they want to use them in applications, and we'll talk about applications today to error correcting codes and derandomization. And almost always in these applications, what you really want is an explicit graph. So why do I say explicit? Well, that's in contrast with a random graph. So as I'll mention shortly, if you just choose a random graph with n vertices and big O of n edges, with high probability it will be highly connected. So that seems to be like a good expander graph. But when people are talking about expander graphs, they don't like these randomized constructions. They usually want an explicit, deterministically created graph. Okay, so those are the three high-level components of expander graphs, and we can be more precise, and we will, but let's talk about them a little bit more in turn. I'm actually going to start with property 2 here, sparse, because it's the easiest one to talk about. So what does sparse mean? Well, I should mention that when in the context of expander graphs, we'll be talking about n vertex graphs, and as always in computer science theory, usually you don't just want, one graph or an expander graph on 1,000 vertices. Generally, you want to talk about families of graphs, graphs on larger and larger number of vertices. You want to say you have an expander graph family if you have, a sequence of graphs on a larger and larger number of vertices n, which is somehow sparse, and each graph is somehow sparse and highly connected. So what I mean by that in more detail is the following. We're going to focus our attention only on regular graphs for simplicity. That's typical in the study of expander graphs. As we saw in the spectral graph theory lectures, everything is 50% more pleasant and simple if you focus on regular graphs. So we will. So we'll be talking about deregular graphs, and the sparsity will refer to the fact that we'll typically insist that d is an absolute constant, which I can write as order 1, and this is with respect to n going to infinity. Okay, so you should really think of d as like a universal constant, like 3 or 10 or 50, that you fix, and then you're going to consider larger and larger graphs, each of which is, deregular. So in particular, if you have a deregular n-vertex graph, it means the number of edges is, well, I guess it's d times n over 2. Let me write it like this, d over 2 times n. Okay, so what it means is if you have an n-vertex graph, the number of edges is a fixed constant, d over 2 times n. So as I said before, we think of these as graphs with a linear number of edges. Okay, so that's sparse. Take that off. Let me talk a little bit now about highly connected. Okay, so what do I mean by highly connected? Well, again, there's a few ways you could quantify this. One way we could quantify it, in fact, is using this notion of minimum conductance from the previous lectures. So we looked at there, phi g, this was the minimum conductance. This was the minimum over all sets of vertices S, whose size is not 0. And we look at up to half the number of vertices in our set S of the conductance of S. And what was the conductance of S? It was the fraction of edges, like UV with U in S and V outside S, divided by the fractional size of S, the fraction of vertices in S. Okay, so this was some measure of, in the regular case, if you were going to take a random vertex from the set S and take one random step from it, what is the probability that step would take you outside S? Okay, so it's the conductance, could also be called the expansion of the set S. It's the probability you get outside the set S when you take one random step from one random vertex in S. Okay, so it's a number between 0 and 1. And, the set has good expansion if this number is big. And this phi g, the minimum conductance of the graph, looks at the minimum of this expansion over all sets of vertices S of size between 0 and half the vertices. So here's a picture. This is the graph G. And this is the set of vertices S. Okay, if you're interested in sets of size bigger than n over 2, then you should really look at the complement set. And we're sort of looking at the fraction of edges that do this, that are on the boundary of S, divided by the number of vertices that are in S themselves. Okay, we want this to be large. And one way to say that the graph is highly connected or a good expander is just to say that the condition might be phi of g is at least 0.01. Okay, or you can, fix some absolute constant epsilon that's bigger than 0, like 0.01 or 0.1, and insist that this minimum conductance be at least epsilon. That would be an epsilon expander. On the other hand, what I want to say is it's best to not necessarily be too picky at this stage at the exact definition of expansion. I should have added, by the way, that the idea here is you fix an absolute constant, again, like 0.01, and then you want larger and larger families of graphs that all have this conductance being at least this absolute constant independent of n. Okay, let me go back to what I was saying. It's not best to be not too picky about the exact definition. So here we kind of looked at the number of edges on the boundary of S divided by the number of vertices in S. That's called edge expansion. But it's also reasonable to look at the number of boundary vertices for S. Let me make that, divided by, the number of vertices in S. So a boundary vertex is just a vertex that has at least one edge into S. Okay, it's not quite the same concept as boundary edges because like a vertex on the boundary of S could have more than one edge going into S. But it's pretty related because we're focusing on d-regular graphs where d is constant. So the number of edges touching each vertex is at most a constant, so it can change these ratios by at most d. So, hoping that this concept, this quantity, the fraction of vertices, let me just make it white, is at least some absolute constant epsilon, is another reasonable way to define expansion. One more thing that's being a bit flexible. You see, it's in some sense harder to have good expansion the bigger the set S is. If you have the expansion of the edge expansion of one vertex, it's always 1, which is as good as possible because the probability of escaping from that vertex is 100% in a random walk, unless you have self loops, which we're going to ignore also here. But the larger the set is, maybe the harder it is to expand. So maybe sometimes you're a little bit flexible on insisting that this size of the set go all the way up to half n. Maybe you only want, sometimes you only want expansion of sets S with, I don't know, S at most 0.01 n. Okay, again, where this is some fixed constant. Okay, so these are notions of highly connected. We'll make some of them even more precise later. So far, I've said that we want graphs or arbitrarily large graphs, large n graphs that are sparse. Every vertex has a constant number of neighbors, it's deregular, and which are highly connected. And it's not too hard to show that random graphs have this property. It's actually just a simple application of the probabilistic method, especially if you're not trying to get too picky about the parameters. So this was an idea due to Pinsker in 73. You can show something like the following. Fix any d that's at least 3, and then there will exist some, let's say epsilon 0, which depends on d. Well, let's just call it epsilon, and it's strictly positive. So if d is 3, maybe it's 0.0001. If d is 10, maybe it's 0.001. Let's not get too excited about the parameters. Such that for all n greater than or equal to some constant n0, which also depends on d, a random n vertex deregular graph is like an epsilon expander. So let's just say has this minimum conductance or minimum expansion at least epsilon. So that is a theorem that's not too hard to prove. It's sort of the probabilistic method. It's mildly easier to prove when you're talking about bipartite expanders, which I'll talk about shortly. But anyway, it's still not hard to prove. For every set S that you're worried about expansion, you also consider every small set T, which might unfortunately have the property that it captures all of S's edges. But you show that in a random deregular graph that's very rare, and it's so rare that you can even union bound over all pairs of sets S and T. Okay, so this simple theorem shows that arbitrarily large expander graphs exist, even for degree d as small as 3. By the way, you cannot make the degree much smaller than 3. Well, any smaller than 3. If you take a random 2 regular graph, like what's a 2 regular graph? Well, it's just a collection of cycles. So if you take a random 2 regular graph, first of all, it probably won't even be connected. And even if, like, by a miracle it's connected, it's like one giant Hamiltonian cycle, this has very bad expansion, because if you take, say, half of the vertices for your set S, then, they have a linear number of vertices, but only 2 edges on the boundary. So their conductance is proportional to 1 over n. Okay, but 3, as soon as you have a 3 regular graph, you have the opportunity to be an expander, and in fact you are if you choose the graph with high probability. Which leads me to the final desiderata, which is explicit. So having these sparse, highly interconnected graphs is great for applications, but often you don't want just a random graph. You don't want just the existence of a highly connected sparse graph. You really want, you want to say, like, here's my n, you deterministically give me a graph on n vertices, that's a great expander. Yeah, let me say here, explicit means that the graph's, let's say, adjacency matrix or adjacency list, G on n vertices, should be constructible in deterministic polynomial in n time. Okay, so yeah, it's not just a randomized existence proof. You can really, get your hands on an n-vertex expander graph in deterministic polytime, and that's quite useful for applications. In fact, believe it or not, there's even stronger notion of explicitness, which will be crucial for some applications, such as applications in derandomization. Let me say what that is. So to say that some graph families are strongly explicit basically means that in deterministic polynomial time, you can construct a graph on 2 to the n vertices, which is a good expander. Now, you have to think a little bit about what that means. How can you, in polynomial time, create or describe a graph on 2 to the n vertices? Well, you describe it implicitly. You describe it by an algorithm that can compute, let's say, the adjacency list situation in polynomial time. So what this really means is, given n, you can have an algorithm that takes as input the name of a vertex, u, and a number between 1 and d, representing like the index into a neighbor, and outputs, you want your deterministic algorithm, the ith neighbor of u in the graph in poly log n time. And it should be deterministic. Okay, so graph family is strongly explicit if you have some algorithm that it's sort of like the algorithm is, I'm thinking of a graph on exponentially many vertices. Well, let's write this as a capital N. Think of capital N as extremely large. The algorithm can take in the name of a vertex, which requires only log of capital N bits to write down, plus this number between 1 and 3 if d is 3. That's not a big deal. And it tells you the name of the ith neighbor of the vertex u, which is also a log capital N bit string. And it does it all in poly of log n time. Okay, so in some sense, it means you have access to an exponentially large graph, even though you're a polynomial time algorithm. Okay, so what are we going to do in this lecture? I'm going to make all of this a little bit more explicit, and we're going to first actually talk about some applications of expander graphs without yet knowing that explicit good expander graphs exist. And then after that, I'll show you some things about the art and science of constructing explicit expander graphs. So before I get into the applications, I want to mention like one completely concrete kind of an expander graph that will be useful for the applications. And this kind of expander graph will be a bipartite twist on what I've talked about so far. So let me give you the picture here. So this is sort of a bit of a bipartite expansion twist. So in the bipartite expanders I'll talk about, you have a bipartite graph with one vertex set u and the other vertex set v. Okay, you can think of them as both having n vertices. And to be a good expander is similar, but we're only going to talk about left expansion from left to right, and regularity from left to right. So we're going to be looking at graphs that are left regular, so each vertex on the left has degree d. And to be a good expander will be to say that for every set of vertices S here on the left side, as long as you're at most, I don't know, a constant fraction of u, the size of u, when you look at the neighborhood, sorry, this diagram is a little confusing, but if you look at this, which is the, what I'll call the neighborhood of S, that's all the vertices that have on the right, which have a neighbor back in S. To be a good bipartite expander is to say that the cardinality of the neighborhood of S is at least some, epsilon fraction of the cardinality of S. Okay, so if you have a set S, in principle, the neighborhood set could be of size d times cardinality of S if like every single vertex in S went to d completely disjoint neighbors. But we won't be that greedy. We'll just hope that the neighborhood set of every set S is at least a constant fraction of the size of S. For all sets S of size, some constant fraction up to a constant fraction of the vertex size of U. Oh boy, actually I've said this wrong. What I really want is, oh no, I've said it right, no problem, never mind. Great. So this is like a slight twist on expansion, but a similar concept, and I bring it up. It's a little annoying to have to bring it up, but it'd be easier just to focus on the first, notion of expansions for regular generic graphs and conductance. But this will be the version that's like convenient to explain the applications. Let me even focus on one explicit set of parameters so that we can have it on hand when we talk about applications. And here's the picture that you should have. So actually, I think a person called Basiligo showed that bipartite expanders of the type I'm about to mention exist if you pick them randomly. So in the parameter setting there, we have n vertices here and n vertices here. And we're looking at expansion. We have a deregular graph. We're looking at expansion from left to right. And we can fix any d to be at least 64. And Basiligo showed that for any d that's at least 64, the size of the neighborhood set of S is at least 0.8 times d times the size of S for all sets S of cardinality at most 0.02 over d times n. Okay, so let me just comment on this. It says you can have d, any fixed constant that's at least 64. Great. And this amount of expansion is quite strong. As I said before, if you have a set S on the left, it expands to the right. The maximum possible number of vertices in the neighborhood set is d times cardinality of S. So this expansion is great. It's 80% of that. And it even works for all sets S of size up to some, constant, small constant, 0.02, divided by d times n. And this divided by d is also necessary because if you're insisting that the expansion be like a constant times d times the size, there are only n vertices on the right-hand side here. So up to constants, you can't do better than this. Okay, so as I said, Basiligo back in the 70s actually showed that with these specific parameters, random bipartite graph, where just for every vertex on the left here, you pick d random neighbors for it on the right, has these properties. In fact, for application reasons, I'm even going to mention that you can have a slightly smaller size set of vertices v on the right. This is u. This is v. For the application I want to show, I want the size of the vertex set on the right to be a little bit smaller than the size of the vertex set on the left. So I'm going to pick it to be size 3/4 n. And notice that that makes my life even harder if I want an expander, because the right-hand side is now smaller. There's like less space for the right-hand side vertices to expand into. Okay, so it's even cooler if I can make the right-hand side 3/4 n. And great. I think if I did the calculations on my paper right earlier today, Basiligo showed that a random graph with all these properties, a random graph, a deregular graph, has this property with high probability when the vertex sizes are n and 3/4 n. And if I got those numbers a little bit wrong, don't quote this lecture for exact numbers. So this is the kind of bipartite expander graph that I'm going to show you can be used to get two cool applications. One application in coding theory, and one application in derandomization. And for both of these applications, Basiligo's result that a random graph has these properties is not good enough. Particularly for the derandomization application, like by definition, if your task is derandomization, you don't want to do anything randomized. And also for efficiency and practicality in coding theory, you also don't want like random codes, you want explicit codes. So that's sort of motivating, the desire for explicit bipartite expander graphs like this. And one might ask, okay, well, do we know how to explicitly get these kinds of bipartite expanders that I tell you are so useful for applications? And roughly, the story is as follows. Roughly, thanks to technology developed over the last couple decades, I would say for almost all expander variants, bipartite, not bipartite, edge expansion, vertex expansion, we know explicit constructions that almost match what randomized constructions get. That almost match parameters of randomized constructions. Okay, so I put almost in quotes there, and you kind of have to check the literature if you want really strong close matching of your favorite particular expander variant. But generally we have very good explicit expanders, and I'll talk a little bit about how we get them the last part of this lecture. But let me just mention that for this explicit case, where I told you I'm going to show you some applications, okay, we don't have explicit expanders that achieve exactly these parameters, but it comes close. So what I will tell you is we do have explicit constructions where, let's say, d equals 64, and instead of this 3/4, maybe you have 0.9999 times n, and instead of this 0.02, maybe you have 0.00001, but that's it. Actually, notice that I did not change this 0.8. We can really get the number 0.8 there. You can really get any fixed constant that's less than 1. And for one of the applications, it'll actually be important that 0.8 is bigger than 0.75. But okay, these two other constants, they're not so important. They make some of the parameters worse, but it'll be fine for us. Okay, so we just to say we do have explicit constructions of these kind of bipartite expander graphs, which are going to be good for these two applications I'll show you in coding theory and derandomization. Okay, so let's move to application number 1 of having these nice bipartite explicit expander graphs. So let me just remind you again the expander graph, the bipartite expander graph that we're going to assume we have for the first application. And this first application will be in the theory of error correcting codes. So once again, we're going to imagine we have, we can deterministically construct in polynomial time an expander graph with 2 sets of vertices. It'll be a bipartite expander graph. On the left-hand side, we'll have some n vertices. And on the right-hand side, we'll have slightly fewer vertices. I'll call this set of vertices R, and here we had 3/4 n vertices. And let's also fix the degree to be the minimum amount that was allowed, which if you recall was 64. So we'll assume that every vertex on the left has degree 64. And the vertices on the right, let me draw them here. We don't necessarily know anything about their degrees. Okay, so we're only assuming this is a left regular bipartite graph. And what is the condition on what is the expansion condition on this graph that we know? The condition is follows. Let's assume we have any subset of vertices over here, S. And S can be any set of vertices as long as it's not too big. It also cannot be the empty set. So let's assume that the cardinality of S is not 0, and it's at most, well, some small fraction, let's say 0.2, divided by the degree, which is fixed to be 64, times n. Okay, so for any subset of vertices like that, what we're going to do is we're going to look at all the vertices that they're connected to on the right-hand side. We'll call that the neighborhood of S, n of S. All the vertices on the right-hand side connected to vertex S on the left-hand side. And the expansion condition is that this neighborhood set is quite large, always. So its cardinality, well, the most it could possibly be is cardinality of S times 64, the degree times 64. And what we're going to, the condition of the expansion condition we assume is that it's a good chunk of this. It's at least 80% of this, 0.8 times the degree 64 times cardinality of S. Okay, so just to remind you, it's now known through the art of deterministic construction of expander graphs that we can deterministically efficiently construct bipartite graphs that look like this. Maybe this 0.02 is a bit smaller, and maybe this 3/4 is a bit smaller, but something like this. These parameters can definitely be achieved, at least with a random graph. Okay, and now let's talk about application number 1. So application number 1 of these kinds of graphs are two good error correcting codes. So let me remind you briefly about error correcting codes. So we're going to be constructing error correcting codes which map some, they're going to be binary codes, so they'll be using zeros and ones. They'll be map some string of length k to a string of length, a bigger string of length n. And what we want is, for it to be good, one thing we want is that n is not too much bigger than k. So ideally for quote unquote good codes, you want n to be just a constant factor bigger than k, so not too much redundancy. And the other desideratum that we want for a quote unquote good code is that it has a very good minimum distance. So any two code words should be at least far apart as some absolute constant times n. So constant factor relative distance, which means you can always correct the number of errors that's up to half the minimum distance. So this will mean, if you have a good code, that you can correct a constant fraction of errors in the n-bit received word. And what we'll see is, essentially, as soon as you have these expander graphs with these parameters, you immediately have a good error correcting code, which is quite hard to find in general. Furthermore, we'll actually see, not just to give you a good error correcting code, of course it's an explicit one, efficiently constructible, and will in fact have extremely efficient decoding algorithms. So that's another beautiful feature of these expander-based codes. Okay, so before I get into saying exactly why these bipartite expanders give you good codes, let me just prove to you one small fact about such bipartite graphs. I'll call this claim 1. So we're going to have two claims in this little story. And it's the following. Suppose you have any set of vertices, S, which has this condition that it's not the empty set, and it's at most 0.02 over 64n. Here I refer, S should be a subset of the left vertices, L. Then what I want to say is it has at least one vertex V in its neighborhood set, which is a so-called unique neighbor. Okay, so what do I mean by that? What I mean by that is just that it, V, which is a vertex in R, has at most one neighbor back in S. Okay, so let me draw you a little picture. Maybe here's S, maybe here's some vertex V, and perhaps this is the unique neighbor for S, or a unique neighbor for S. Again, what does that mean? Well, V has some edges back to L, and the property of being a unique neighbor, we know it has at least one edge to a vertex in S, because V is a neighbor of the set S, but being a unique neighbor means it has exactly one. Okay, so let's prove this little claim. And the way we'll prove it is Well, let's assume for the sake of contradiction that every v in the neighborhood of S has at least two neighbors back in S. Okay, so it has no unique neighbor. What we're going to do is now count the number of edges touching S. So on one hand, since we have just decided that every vertex V in the neighborhood of S has at least two neighbors in S, that means sort of each of these vertices V in neighborhood of S, contributes or donates or, is associated to two distinct edges which touch S. So by virtue of this assumption, we conclude, that there are at least, so many edges touching S. And what is this so many? Well, I just told you there's at least 2 for every vertex in the neighborhood of S. But by assumption over here, we know that this is at least 2 times 0.8 times the degree, 64, times the cardinality of S. And the key point here is that 2 times 0.8 is bigger than 1. Okay? Nothing more special than that. So this is, let's say, strictly greater than 64 times the cardinality of S. But this is indeed a contradiction. Why is it a contradiction? Well, I mean, this bipartite graph is left regular with degree 64 on the left. So the maximum number of edges that could be touching S is 64 times cardinality of S. So that's a contradiction. And it completes the proof of this little claim. Okay, great. So let's put that claim in the bag. We'll need it for our analysis. And now I'm ready to tell you how to get a good error correcting code out of this bipartite expander graph. And the idea is really quite simple. I'm going to define the code. It's a binary code of block length n by specifying that its parity check matrix, H, is basically the adjacency matrix of the graph. Well, not quite the adjacency matrix. I don't literally mean view the graph as a full graph in the adjacency matrix. I kind of mean the bipartite adjacency matrix. You'll see what I mean in a second. So what I'm saying here is this parity check matrix for the code, H, it's going to be in F2 to the R cross L. It's a little bit backwards, but R cross L. So this parity check matrix, H, will look like this. It'll be indexed by the it'll be indexed by the right-hand vertex set, R, and the columns will be indexed by the left-hand vertex set, L. Remember, this is 3/4 n vertices, and this is n vertices. Okay, here's the picture back up here. So the rows will be indexed by the right-hand vertex side. The columns will be indexed by the left-hand vertex side. And, right, so we'll just it'll be a 0-1 matrix, and we'll put a 1 in an entry if there's an edge from that vertex on the left to that vertex on the right. So in particular, if you think about it, for every column, because it's regular on the left, for every column, we'll have 64 ones in here, in each column. Okay, and what does it mean for this to be the parity check matrix? Well, I'll remind you once in coding theory terms, and then I'll also sort of give you like a picture involving the graph. So what does it mean for a matrix to be a parity check matrix? It means that if we look at any received word, z, okay, so let me call this z. This is in F2 to the n. Z is a code word if and only if hz equals 0. Okay, that's the definition of the parity check matrix. Hz is the 0 vector of 3/4 n height. Okay, so z is a 0, 1 vector, and these h's rows are 0, 1 vectors as well. And each of them you kind of dot product against z, and to be a code word, all these dot products should be 0. Now let me explain it to you with the picture. If you think about that, what does it mean? Let me try to get rid of this orange stuff here. What it means is, you see, given a received word z in f2 to the n, you can think of it as being, its indices as being labeled, its indices as being associated with the vertices of L, and therefore you can think of the code words bits as like labeling the vertices of L. So z1, z2, up to zn. Given a code word, these are like 0, 1 entries, labeling the vertices. And now, each row of the parity check matrix, each parity check is associated with the vertex on the right-hand side. And we don't know anything about its degree, remember, but I mean, it has edges to some vertices back in L. And it's a parity check in the sense that the constraint is that the parity or XOR of these bits should be 0. That's exactly what's going on with this matrix scenario. So to say that for every row, let's say that hz is 0, is to say that for every row of h, if you dot it with z, mod 2, you get just the number 0. Well, mod 2, that's exactly saying that for every vertex on the right here, if you look at its neighbors back in S and just add up mod 2, the labels that z gives to them, those should add up to 0. Okay, so you're a code word z if when you put your bits onto the vertices of L, they satisfy all the sort of parity checks or XOR checks implied by the right-hand side vertices. Great, so that's the definition of the code. And it's a linear code, it's a linear subspace. So what are the two things we always want to know about a code? We want to know about its rate and we want to know about its minimum distance. So its rate is easy to work out, or its dimension is equivalently. So the dimension, or the quote-unquote k for the code, well, if you recall, for linear codes, it's just going to be n minus the number of parity checks, 3/4 n. Okay, and that's kind of easy to see because each parity check is like a linear constraint on z. And so every time you insist on a parity check, it kind of knocks out one dimension. And we have 3/4 n parity checks, so the z's that satisfy all these parity checks will form a subspace of dimension 1/4 n. Okay, and this is the thing that's usually called k. And this is great, this is wonderful, because it means the rate, which is k over n, is a quarter. And that's wonderful. That's a nice big number. It means n is just 4k, so if you want to encode a message of k bits, you only use 4 times k bits to encode it. So that's great, just a blow up of size 4. Okay, so it's got a good rate. That's one of the criteria we need for a so-called good code. And the other thing we need is a good minimum distance, okay, which means all the code words are far apart in Hamming distance. And one thing you may recall about a linear code is that there's a nice characterization of its minimum distance. It's also the minimum Hamming weight of any non-zero code word. So in a linear code, the all zero string is always a code word. It always passes all the parity checks, of course. So what you want to do is you want to look at the non-zero code word that has the lowest Hamming weight. And its Hamming weight is the minimum distance of the code. Okay, it's at that distance from the 0 code word, but also it's not hard to see that like every pair of code words has to be at least this Hamming weight apart. So my claim is that the minimum distance of this code is actually greater than this quantity 0.02 over 64 n, this upper bound and the allowable set size s that you can apply the expansion guarantee to. And if I prove this claim, that's also super great because this is indeed a constant fraction of n. It means you can correct up to half this number of errors in your error correcting code. So you can correct 0.01 over 64 n many errors. And that's a constant fraction of n. So that's great. That's what we're looking for. Okay, so to prove this claim, it's going to be easy. I'm going to use the other claim, claim 1 as I called it. I suppose this is claim 2, but anyway. Okay, so as I said, the minimum distance in this linear code is the minimum weight of a non-zero code word. So let me just lazily do this by contradiction again. So let's assume for the sake of contradiction that z is an n-bit vector, which is not the 0 vector, and it's a code word, and its Hamming weight is at most this 0.02 over 64n. Okay, and now, of course, you may have guessed this, we can think of z is the indicator, as the indicator, the 0, 1 indicator of a subset S of the left vertex set. Remember, when we have a received word z, we can always sort of label the vertices of the left set by the bits of z. And, you know, all the bits labeled 1 we think of as the subset S. Okay. And now you may not be surprised as to what we do next. We apply claim 1. And claim 1 tells us, therefore, that this set S, okay, it's not the empty set because z is not the 0 code word, but it does have size at most this key bound. Claim 1 tells us that this set S has a unique neighbor, one of these unique neighbors in R. Call it V. Not really sure we need to call it anything because let me just show you what happens in the picture now. If we go back up here, let's imagine this orange square here was V, this unique neighbor. Oh, it can't be because this neighbor has two vertices, two neighbors back in S. So let me erase this one. Okay, so now, yeah, now this V could be a unique neighbor. Oops. Yeah, well, it is in the neighborhood of S according to this picture. Let me extend the neighborhood of S here, hypothetically. Okay, so this vertex V is a neighbor of, gosh, I guess it's not. Let me extend S as well. Great, I think I've finally drawn the diagram nicely. So here's S, and this vertex V here is a unique neighbor in the sense that it's a neighbor of S, but it has no other edges that go into S. And now let's just think about the parity check associated to this vertex V. Well, this parity check is just, XORs together all the labels of Z that Z gives to the vertices which are neighbors of V. So, this one, and this one, and this one, and this one. But remember, the set S is all those positions, or all those vertices where Z has the coordinate 1. So it means that, the label here is 0, and then this one is 0, and this one is 0, and all the edges that go to something not in S get 0. But, the single unique edge that goes back to S gets 1. So the XOR is 1, which means the parity check did not pass. So that proves it's not a code word. That's the contradiction. Or if you want to think about it this way, I'm not sure if this will help that much, but if this is the row associated to V, these sort of dots, let me say these yellow columns are the ones where Z has a 1, which is equivalent to the set S. Then what we just showed here was that, there's a unique 1 here, there'll be 0 in all these other S rows, and there could be 0s or 1s elsewhere, but it doesn't matter, because when you dot product this row with Z, you just pick up these products, or these bits, so you get exactly 1. Okay, I suppose the picture was clearer. Okay, so it has a unique neighbor in R, call it V, and then by our picture argument, it implies that the parity check associated to V does not pass, contradicting Z being a code word. Okay. So, great, that's it. So this shows that once you have this expander graph, this bipartite expander graph, you automatically get a good code for it. And you can deterministically efficiently construct it given n, so that's great. And it's always nice to have a linear code that you can efficiently construct, because then encoding is very easy. Well, you have to actually work out the generator matrix for that. I wrote a little Piazza post about how you go from the parity check matrix to the generator matrix, but basically it's you take out a few columns and then take the transpose. And it's very nice to have you know, linear code, a generator matrix, because then encoding is easy. You just it's just a matrix vector multiply. And what about decoding? So actually that turns out to be another beautiful aspect of these expander-based codes. All of the things I'm saying, by the way, I forgot to mention it, but they originate in well, papers by Tanner and also Spielman and Sipser and Spielman from '96. And one thing they proved, which I will not prove to you here, maybe it'll be in homework, but it's quite easy, is that this code has polynomial time, poly-n time decoding from up to, you know, half the minimum distance. So from less than d over 2 errors, where I've written capital D for the minimum distance. Normally you write little d, but we use that for degree in graph. So yeah, this algorithm, or this code, has an efficient decoding algorithm that takes any received word, which has fewer than minimum distance over 2 errors, and finds the nearest code word. Just a couple of comments on this. First of all, this very simple algorithm crucially uses, I mentioned this before, but it really uses that 0.8 is greater than 3/4. Okay, so this 0.8, which was sort of the amount of expansion that we got in our neighbor set sizes, was quite good expansion, and we rely on the fact that it's bigger than 3/4 to get this fact about decoding. Another great fact is that if you're actually very careful, you can take this poly-n time and make it linear time. Okay, so that requires more work than this argument that is easy and perhaps will be on homework. That one's not as easy, but that's the beauty of it, that this is not only is it a good code, but has a super fast linear time decoding algorithm, which is also wonderful. And let me tell you one more wonderful thing. I'll just tell you, not the super fast algorithm, but a polynomial time decoding algorithm. It's so easy, I will write it for you here in 2 lines. Here's a decoding algorithm. That's polynomial time. Here it is. You're given z, the received word, and let's assume it differs from a code word in at most d over 2 places, and we want to find that code word. So here's the algorithm. It's a while loop. While h times z does not have Hamming weight 0, flip any bit of z that causes this Hamming weight to decrease. Okay? So, you know, if you get down to the case where h times z has Hamming weight 0, it means it's the 0 vector, which means it's a code word. And if you're not at a code word, then just go through all the bits of n and try flipping them and see if that decreases, you know, the number of failing parity checks. If it makes more parity checks, accept. And if flipping a bit causes a parity check, well, more parity checks to accept than it causes to break, so it makes the overall number of successful parity checks go up, then just do that flip. That's it. That's the whole algorithm. And the analysis that it, in polynomial time, gets to a code word within distance d over 2 is not that hard. It's like a page long. Maybe even that could be homework, who could say. This is an example of a simple belief propagation style algorithm. And yeah, the fact that it works, again, relies on the expansion properties of the bipartite graph. Okay, so now let me tell you about a second application of these bipartite expander graphs that we've been talking about. And this one will really use heavily the fact that we have explicit, deterministic, and even fully explicit constructions of expander graphs, because the topic is derandomization. Okay, so this is application 2, derandomization. So we talked about derandomization some already in this course. And what I'm going to show you now is how it's almost like a little magic trick you can do if you're not interested in fully derandomizing an algorithm, but simply getting better probabilistic guarantees about your algorithm without using more random bits than you need to. And as I said, it's a bit like a magic trick. You'll see that like we get something for nothing almost from these expander graphs. So to set this up, let's set the stage for a very simple randomized algorithms derandomization problem. So let's say that A is a randomized algorithm with one-sided error, so like an RP style algorithm, error for a decision problem P. And normally I don't like to use the letter P for a decision problem because it reminds one of complexity class polynomial time. But let me stick with it, P. And one reason I chose the letter P is an excellent example is the decision problem primality. So imagine this randomized algorithm A is trying to decide if a given number is prime or not. And the Miller-Rabin algorithm, the most standard primality testing algorithm, is a randomized algorithm with one-sided error. It has the property that, well, before we get to the property, let's imagine this viewpoint of a randomized algorithm. One way a viewpoint of a randomized algorithm A is, it gets in the true input X, and, it outputs yes or no. And it flips some coins as it's doing that, and it gives the correct answer with high probability. But it's also nice to think of this viewpoint where A is a deterministic algorithm that gets access to random bits, and that's how we'll think about it again. So let's imagine that A is a deterministic algorithm that gets access to R, a random n-bit string. Okay, so we kind of pull the random bits out of the algorithm, and now, to say that A, solves the decision problem P with one-sided error, and we'll assume it has error 1% for this example, we'll assume that has these properties. So if X is a yes answer, if X is in the language, think of primes again, then when you choose the random string R, uniformly at random, the probability that you get the yes answer out of A when it's fed X and R is 1. Okay, so if X is in the language, it'll always say yes, and if X is not in the language, then the probability over R that you get the wrong answer, yes, is at most, as I said, 1% or 0.01. Okay, and this is kind of like how the Miller-Rabin algorithm behaves. If you give it a prime, it will always say prime, and if you give it a composite number, it might possibly rarely accidentally say prime, even though it's composite. Okay, so what we want to imagine for this sort of little derandomization magic trick is that we want to reduce this error without using any more random bits. Or without, let's say, conserving random bits. Okay, so we'll imagine that like random bits, like randomness is like super precious. And so we really want to use very few random bits, but we want to decrease the error. So let's also say that A is an algorithm that takes time t. So one thing you can do to reduce error is the thing that you always do to reduce error. Just repeat the algorithm a bunch of times, and in this case, say yes if and only if all the answers were yes. Okay, so that's the standard thing to do. You could repeat, let's say, d times the algorithm independently with fresh random independent bits each case. And what would happen? So you would use d times t time, and you would use d times n random bits. Okay, we're assuming that each run requires n random bits. And what is the error probability of this repeated algorithm? Well, it's 1% to the power of d. Okay, and that's the classic standard error amplification or error reduction thing. If you pick d to be, 100, that's pretty good. You take 100 times more time, and your error probability goes way down. But you have to use 100 times as many random bits. And, in this little example, I want to really focus heavily on conserving random bits. So I'll consider that quite expensive. So here's the second strategy that uses fully explicit expander graphs. And what we're going to do is take one of these bipartite expanders of the type we've been talking about, this bipartite expander, but on 2n plus 2n vertices. Okay, so I'll explain what I mean by that just now. But what I'm saying is, well, actually, these bipartite graphs we talked about before had like, n on one side and 3/4 n on the other side. Just ignore that 3/4 thing. Let's assume they have the same number of vertices on the left and right. But let's assume that same number of vertices is 2 to the n. Now, this is like, I'll put an exclamation mark here because this is a bold move. What we're relying on here is this strongly explicit property. Okay, so let me remind you, what does that mean? We're assuming these bipartite expanders are strongly explicit, so we don't literally like write down the adjacency matrix of this bipartite graph, vertex set L and R with 2 to the n vertices here and 2 to the n vertices here, but the algorithm sort of mentally knows about it. And what does it mean that it mentally knows about it, this strongly explicit thing? It means the algorithm in polynomial time can understand the adjacency relationship of this graph. So if you're the algorithm and you think of the name of a vertex over here, okay, this is named by n-bit strings. And you also, we'll stick with the D regular graph or the 64 regular graph. If the algorithm thinks of a number between 1 and D, or 1 and 64 specifically, then it can figure out in polynomial and n time, like the names of these D neighbors. Okay, these are also n-bit strings. And the point is that you can work out the neighborhood or neighbor relationship in poly n time. Okay, so this randomness reduction, this error reduction algorithm that conserves randomness is going to sort of take this graph on 2 to the n plus 2 to the n vertices. And remember, once again, what is the property of this, the expansion property of this graph? It's that the neighborhood set of any subset S, okay, so if S is a subset of L, and the size of S is at most, 0.02 over D or over 64 times n, then the number of neighbors of S is at least 0.8 times D times cardinality of S. Okay, so what is the actual algorithm here for trying to decrease the error in algorithm A? So step 1, pick a vertex L on the left-hand side uniformly at random. Okay, and that's picking a random n-bit string, so this definitely costs you n random bits. No doubt about that. But now, just consider its neighbors. Let R1 through RD be L's neighbors. Okay, so these are right-hand side vertices, which are also named by n-bit strings. And by the strongly explicit aspect of these bipartite graphs, where you can compute this neighborhood relationship in polylog the number of vertices time, or poly little n time, this calculation of computing these vertices takes poly n time, which is nice. And now we have D n-bit random strings. So we just run our randomized algorithm A on X with random strings R1 through RD. These are n-bit strings. And we do the usual thing, right? If they all say yes, then we overall output yes. Otherwise, if one of them says no, we can output no. Okay, we say yes if all answers are yes. Okay, and let's do the analysis of this. Well, several things are very good. So this is a poly n time algorithm. In fact, well, it involves t as well. So let's just put that in a box since we're talking about here. The time for this algorithm is, well, poly n to compute these d different strings, plus we ran the algorithm d times, so poly n plus d times t. Okay, so compare that with the naive or standard repetition method. Okay, we added poly n time, but that's nothing too special. And of course, if the string x is in the language, then all of these runs, no matter what random coins you use, because we have one-sided error, all these runs will give you back the answer yes. So you'll overall answer yes, so that's fine. So the only thing we have to worry about is, suppose the string is x is not in the language, what is the probability that will incorrectly overall say yes? Okay, so let's think about this for a moment. If the string is not in the language, then our assumption here is that the probability over our random input for A, random coins for A, that you incorrectly say yes is at most 1%. Okay, and so, we're going to be feeding in for our random strings, vertices from this set R. These are named after n-bit strings. And what I want to do is think of the set B of, the set B of sort of bad strings for the algorithm A. I'll call it set B. And what I mean here is let B, let's do this in white. Let B, subset of R, be the, at most, 1% bad strings, random strings, for A on X. Okay, the ones that cause it to incorrectly say yes, even though X is not in the language. And now, in order to analyze, the probability, we'll use any of those, or we'll use all of those strings. Let's let S be a subset of L be the set of bad choices for little l. Okay, so remember this is little l here. And what does it mean for the initial choice little l to be bad? What it means is that it means that the neighborhood of this vertex L is a subset of B. Right? Because when do things go really wrong? It's when you pick a vertex like this L, all of whose neighbors are in the bad set B. Okay, that seems quite rare, because then in that case, all your random strings R that you use will fall in the bad set B. Remember, those are the strings that cause A to incorrectly say yes, even though X is a no string. Great. Well, it seems there shouldn't be too many such strings, and indeed that's the case. So here's the claim. We claim that the cardinality of this set S is at most this magic bound 0.02 over D times 2 to the n. And why is that? Well, otherwise, if S is bigger than that, well, the first thing I'll do is let me just do something kind of simple. Let me just pare it down to a set of exactly that size. Choose any subset S prime of cardinality sort of exactly 0.02 over D times 2 to the n. Okay, maybe round that to an integer, but let's not worry about that. Okay, so just pare it down to some subset that has exactly 0.02 over D to the 2 to the n strings. And now the point is, like, this S prime is just small enough that we're allowed to apply the expansion hypothesis to it. So this S prime is an expanding set. And therefore, by the expansion property, the size of the neighborhood set of S prime is at least 0.8 times D times the size of S prime. okay, which is 0.8 times d times 0.02 over d times 2 to the n. And just the point here is that the d's cancel out, and this is 0.16 times 2 to the n. And that 0.16 is cooked up to be, well, greater than 1%. So actually greater than 1% times 2 to the n by quite a bit. Okay. But now let's think about this. Every vertex in S, L, has its neighborhood in B. And in particular, every vertex in S prime has its neighborhood in B. So we know that for all L and S prime, the neighborhood of L, that single vertex, is a subset of B. Okay, so that just means that the neighborhood of S prime is a subset of B. But we know that the cardinality of B is at most 1% times 2 to the n, right? Because what is B? It's just the set of bad strings for A. Okay, and by assumption, the set of bad strings for A is at most 1% of all strings. Okay, and now we have our contradiction because, well, of course, this on one hand, we saw that the neighborhood of S prime had size bigger than 1% times 2 to the n, but it's a subset of B, and B has size only 1% times 2 to the n. Okay, so that's a contradiction, and that proves our claim. Great. Okay, so now what do we finally conclude from this? Well, it's that this set S of bad initial choices little l is quite small. It's at most a 0.02 over d, fraction of all initial l. So the failure probability, or the wrongness probability of our algorithm, is bounded by 0.02 over d, the probability that the initial little l is in S. So what we finally conclude here is that for this new algorithm, the derandomized algorithm has error probability at most 0.02 over d. And this is great. So, I mean, if you, well, because in particular, it only uses n random bits. Okay, because the only random bits we needed were to choose this initial L. Okay, so let's compare it. What we have is, okay, we have polynomial in n, which is fine to assume, plus d times t time. So it's roughly the same as like the naive algorithm that just repeated d time. And we use only n random bits. So this is why I think it's like a magic trick. Like, we didn't use any more random bits than just a single run of the algorithm needs, which is kind of amazing. Compared with the naive algorithm, which uses d times n random bits. And okay, we don't get the error probability down to 1% to the power of d. We get it down to more like constant over d, rather than exponentially small in d. Okay, we get it down to 0.02 over d. Okay, so that's, if d is 64, then we got it down to 0.01 over 32. So we, took a factor of 32 off the error probability, while only increasing the running time by a factor of, 64. Okay, so in general, you get like linear error decay as a trade-off with the amount of time you use. But kind of amazingly, you use no more random bits. So that's kind of amazing. Let me end here by, this is kind of a somewhat simple way to use expander graphs to do derandomization. There's a bit of a more standard way that gives you, can give you this exponential error decay. So let me just put this as a remark. If you use a similar idea, but you take like a very large expander graph, not necessarily bipartite, but think of just a regular usual graph on, again, 2 to the n vertices. So you need fully explicit expander graphs. And so each vertex name is like an n-bit string. You can take like such a graph with, let's say, regularity 8. So every vertex has 8 neighbors. And then what you can do is you can generate a bunch of n-bit random strings by picking one initial random n-bit string, like we did, paying n bits, and then doing a random walk. And as you do each step of the random walk, you only have to choose a neighbor, so you only need to pay 3 bits of randomness, if the regularity is 8, to get to a new n-bit string, and then you get to a new n-bit string, and so forth. And you can show, actually, that this achieves sort of the exponential error decay. So let me write this. Using this idea of like a length t, random walk on a non-bipartite, let's say 8 regular. Just pick that because it's a nice power of 2 bigger than 3. 2 to the n vertex expander graph, which of course you need a fully regular expander graph to get that. You'll use, again, as you take this random walk, you collect up t n-bit random strings, and then you run your randomized algorithm A using each of them and say yes if and only if all of them say yes. You use n plus 3t random bits. Let me just write it as n plus order t random bits. Those pluses and t's look similar, so n plus order t random bits, n plus 3t random bits. And you can show that the error actually goes down exponentially. It's like at most 2 to the minus theta of t. Okay, so it doesn't go down just like 1% to the power of t, but it goes down like some constant to the power of t. And I won't prove this, although it's not too hard. The analysis is extremely similar to the analysis we did in the last lecture about how random walks in an expander graph, or a graph that has its minimum conductance large, or its second smallest Laplacian eigenvalue large, mix very quickly. So the analysis is very similar if you want to prove this fact. And not only that, this is about, the way I've described it is about reducing error in one-sided error algorithms. But this can also be proved for two-sided error algorithms. You can equally well take them, and at the cost of n plus order t random bits and t repetitions of the random algorithm, reduce even a two-sided error algorithm down to two-sided error that's exponentially small in t. Okay, so in the last part of this lecture, having shown you some applications of expander graphs, explicit expander graphs, I'm going to start talking about actual constructions of explicit expander graphs. And there's actually several ways to make such constructions, and I'll survey them a little bit. Unfortunately, there won't be time to actually prove that any of these constructions work, but the proofs are not too bad, actually, and maybe we'll explore some on the homework. Okay, I must also confess that I got to do a bit of a bait and switch on you. So in the two applications we talked about, we used bipartite expander graphs, but I'm going to tell you about constructions of regular old non-bipartite graphs, which are expanders. And so let me just briefly tell you how you can take a regular graph with some expansion property and convert it into a bipartite graph with the kind of expansion properties that we use in applications. So I'll just sort of do this by some quick pictures. Let's say you have a regular old graph G. This will be a deregular, not necessarily bipartite graph. And it will always have n vertices. These will actually be two standing assumptions for all the graphs we talk about today. So let's say you have a graph like this and you've managed to show it has some good expansion properties. How can you get a bipartite graph out of it that hopefully has good expansion properties? There's actually two nice methods. So we're trying to get like a new bipartite graph over here. Oops. With some bipartite, with some expansion properties. One method is called taking the double cover of G. And what does that mean? It basically means you take your copy of G, and you take another copy of G, and each copy of G has some edges, and basically you make the edges go across instead of within G. Okay, and if G is deregular, then this double cover will also be deregular. And another way to explain it, an easy way to explain it, is if A is the adjacency matrix of G, then the adjacency matrix of the double cover, it has 2n vertices, so it's twice as big, and it's bipartite, and it kind of looks like this. You put A here, and A transpose here, and 0s here. Okay, so if you think about it, that makes a bipartite graph, which is kind of like the one I just described. So that's one way to turn a regular usual graph into a bipartite graph. And it often gives you the good expansion properties, or preserves the expansion properties. And another way is to make what's called the line graph. And this doesn't give you a balanced bipartite graph, but it gives you something pretty balanced if d is constant. For the line graph, you just make a bipartite graph where one set of vertices is associated with the original vertices v of g, and the other set of vertices is associated with, that's not a very good E, is associated with the original edges of g. And then you put an edge between a v vertex and an e vertex, if and only if that v vertex touches that e vertex back in the graph g. Okay, so each edge is, of course, connected to two vertices. So this graph will have regularity 2 on the right-hand side. And each vertex v is connected to d edges. So you'll have regularity d on the left-hand side. Okay, so let me just leave it at that. That's a couple of ways to get a bipartite graph, which hopefully is a good expander, out of a good expanding usual non-bipartite graph. The other aspect of the bait and switch was, in these bipartite graphs, we talked about vertex expansion, where, for every set of vertices here, let me switch colors briefly, every set of vertices here, if you look at its neighbors, if we call this S and this the neighborhood of S, then n of S had to have large cardinality whenever S was not too big. That's called vertex expansion. But now, when I go back to talking about usual non-bipartite graphs, you can talk about vertex expansion, but it's going to be easier, and it's a bit more common to talk about edge expansion. So let me just write these two things here, edge expansion. So from now on, I'm talking about not necessarily bipartite graphs versus vertex expansion. And so an edge expander is one that satisfies something like this for all sets of vertices S of cardinality at, let's say, most half the number of vertices n. The fraction of edges on the boundary of S is a good proportion of S itself. Or to put it in this probabilistic way, if you choose a random edge uv, the probability that u is in S, given that well, let me just say, that v is in S, given that, v is not in S, given that u is in S, is at least epsilon. Okay, it took me a couple tries there, but what I want to say is that another way to put it is if you pick a random vertex in the set S, uniformly random, and take one step in the random walk, the probability of u escaping S is big. It's at least epsilon. Okay, that's edge expansion. And vertex expansion is a condition that looks like this for all sets S, again, maybe of size at most n over 2, or some constant fraction of n. The cardinality of the vertex neighborhood of S is at least some epsilon times, the maximum it could be epsilon times d, times the cardinality of S. Okay, and as it turns out, in the study of expander graphs, it's more convenient to study edge expansion. It's a little bit easier, but they're not unrelated. Now, in fact, I have to pull one more switch on you, which is that finally in the study of expander graphs, it's even more usual not to study this edge expansion parameter epsilon, but rather to study the second smallest eigenvalue of the graph's Laplacian. Okay, so let me repeat that. It's even more typical to study what you might call lambda 1. This is the second smallest eigenvalue of G's Laplacian, your graph's Laplacian, which, let me just remind you, L, it's normalized Laplacian, it's the identity matrix minus the normalized adjacency matrix. Okay, so we're in the setting of regular graphs now here. So A is the adjacency matrix of the graph, 1 over D is the normalized adjacency matrix, and the Laplacian is the identity minus that. And as we saw in the spectral graph theory lectures, This matrix always has an eigenvalue of 0. That's equivalent to saying that A always has an eigenvalue of D. And what controls the expansion is the second smallest eigenvalue, which we call lambda 1. Okay, and what we saw in previous lectures was this thing Cheeger's inequality, which relates this lambda 1 to the best epsilon you can put here. This is really, the best epsilon you can put here again is this minimum conductance of the graph G. And we know that these two things are related up to a square or up to a square root, depending on how you put it. So in particular, let's say relates this lambda 1 and epsilon. So in particular, actually, it's even harder in some sense to construct a graph whose lambda 1 is big than it is to construct a graph whose edge expansion parameter epsilon is big. This is the easy direction of Cheeger's inequality. If you construct a graph which has a lambda 1 that's large, then, well, in fact, just lambda 1 is at least epsilon. Sorry, wait a minute. Wrong way around. Lambda 1 is at most epsilon. Maybe there's a factor of 2 or a half, or sorry if I'm getting this slightly wrong. But what it means is if you manage to construct a graph whose lambda 1 is large, then automatically its edge expansion is large. And that's the easy direction of Cheeger's inequality. Let me just put a little squiggle here to denote up to a constant factor. The hard direction of Cheeger's inequality is that also if lambda 1 is large, then epsilon, the edge expansion parameter, is also kind of large up to a square. Okay, so this two-sided inequality says that if you're interested in edge expansion, then and you're being a bit qualitative about things, then it suffices to study this eigenvalue. And that's what we'll do, because in some sense, the second smallest eigenvalue has a polynomial time algorithm for computing it, so it's somehow easy to understand mathematically. It's characterizable. Whereas as we saw, this minimum edge expansion parameter, this minimum conductance, is NP hard to compute, so it's hard to get your finger on it mathematically. And so what we're eventually going to talk about constructing, and what everybody or most people when they're constructing expander graphs strive to do, is they strive to get what's called an n, d, epsilon spectral expander. And what does this mean? This means a d-regular n-vertex graph G with second smallest eigenvalue of the Laplacian, lambda 1, at least epsilon. So sorry I'm using the same parameter epsilon here. Let me call this epsilon 0 and this epsilon 0. Okay, and if you have such a spectral expander, then by the easy side of Cheeger's inequality, it's even a good edge expander. You can also show, this is not too hard, that if you have a good spectral expander, it implies you have pretty decent, let me just put that in quotes, vertex expansion as well. This was originally proved by Alone and Millman, and it's a consequence of the tight form of the expander mixing lemma, which we'll mention shortly. But all of which is just to say that I want to convince you that if you can construct these spectral expanders, then they give you, good edge expanders, and therefore, and also good vertex expanders, and also you can get good bipartite expanders, and so forth and so on. So this will be our task for talking about this will be our task for the remainder of the lecture. And let me just mention here that it can also be good to think about the eigenvalues of A, or this matrix K. So this is, let me erase this up here. This was I minus K, where K is the transition matrix for the graph, 1 over d times A. And this K had eigenvalues that we called, let's see, what do we call them? Kappa, I think we called them kappa 0 through kappa n minus 1 as well. And they satisfied, well, they're just 1 minus the lambdas. So they satisfied that 1 is equal to kappa 0, greater than or equal to kappa 1, greater than or equal to dot, 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 greater than or equal to kappa n minus 1. Okay, and so just as L had a trivial eigenvalue of 0, K has this trivial eigenvalue of 1, and so the key parameter is kappa 1. In particular, the key interest is like how far away from 1 it is. So we're interested, we call it, an expander, a spectral expander, when kappa 1 is less than or equal to 1 minus epsilon 0. That's equivalent to this condition on lambda 1 being at least epsilon 0. Okay, that was a little bit messy, but let me now say we're just focused on constructing explicit n vertex graphs that are n d epsilon 0 or epsilon spectral expanders. And as I mentioned before, what we really want to do is fix some d, like a really fixed constant like, I don't know, 3 or 4 or 8 or 50. And then get some epsilon 0, which is strictly positive constant, 0.001 is kind of okay for us. And then what we want is n comma d comma epsilon spectral expanding graphs for arbitrarily large n. Okay, we don't have to get them for every n, but like maybe every n that's a power of 2 or every n that's a square or something would be fine for us. But we want, like a large infinite family of these graphs. And what we really want is for them to be deterministically constructible in poly n time. And what we really, really want is for them to be fully explicit, which kind of means that you could even get like a 2 to the n vertex such graph with its adjacency matrix or adjacency list computable in poly n time. Okay, so on with the show. Let me tell you about 3 constructions. And the first construction, it's really great because it's like unbelievably explicit. It's like so explicit. You just write it down, and the proof that it's a spectral expander is not so bad. So this construction basically originally due to Margulis from 1973. Actually, the day I'm recording this, Margulis won the Abel Prize. So congratulations, Grigory. And thanks for the expander graphs. He's actually going to show up in construction 2 as well. But there's a subsequent paper by Gaber and Galil from 81, which kind of tidied things up a bit. And so, we don't need to give Margulis too much credit. So these are often referred to as the Gaber-Galil expanders. And the nicest analysis of them was done in a subsequent paper by Jimbo and Maruoka. Okay, so without further ado, what is this graph? Family of graphs. So you pick a parameter m, and then the vertex set for your graph, v, will be the integers mod m squared. Okay, so you think of it as like a grid. Here's a m equals 4 example. And, these vertices are indexed by pairs x, y, where x and y are integers mod m. Okay, that's the vertex set. And what's the edge set? Well, you connect a given vertex xy to the following 8 vertices. I have to copy them off my screen here. X plus, yikes, x plus, plus y, comma y. That's the first neighbor of xy. X minus y, comma y. That's the second neighbor. And you also do x plus or minus y plus 1, comma y. That's the third and fourth neighbors. And then you do a symmetric thing. So you connect it to x, comma y plus or minus x. That's the fifth and sixth neighbors. And x, comma y plus or minus x plus 1. And that's it. So d equals 8. And this is a wonderful expander, family of expander graphs, one for each m. So you have an expander graph for every n which is a square. For several reasons. First of all, well, let me just state the theorem. The theorem is that this is an m squared, comma 8, comma, epsilon 0 spectral expander for some strictly positive constant epsilon 0, which, you have to kind of squint into the Gaber-Galil proof or whatever. But I think maybe like epsilon 0, like 0.1 or something. Okay, so the actual expansion parameter is not like amazing. It's 0.1, that's okay. But it's got so many other great properties. Um, First of all, it's, as I mentioned, strongly explicit or fully explicit. I mean, it's as great as you can get. What that means is, there's absolutely no trouble in, like, for a poly n time algorithm, imagining one of these graphs and working with one of these graphs on 2 to the n vertices. Because these, names of vertices are just pairs of, numbers, mod m. So if you can imagine if, like, m is, let's say, 2 to the n, so these vertices are just named by pairs of n-bit strings. And, if I give you a particular pair of n-bit strings, it's super easy to compute the 8 neighbors of these strings. You can do that in linear time, order n time. It's just some addition. So these are brilliant, strongly explicit graphs. The degree is 8. That's very nice. It means if you want to take a random walk in this, even this exponentially sized graph, then, every time you take a step, you use 3 random bits to pick a random neighbor out of the 8 possibilities. So that's great. And that's all I'll say about it. I mean, the analysis of it is kind of a drag, but it's like 2 pages of elementary linear algebra that you can look up online. James Lee and Luca Travisan have good expositions of it, for example. Okay, so that's the first expander I want to tell you about. The second family of expanders I want to tell you about are actually the so-called Ramanujan graphs, and let me warm up to them. So, as I mentioned before, a random deregular graph is an excellent expander. It's got great edge expansion. The only trouble with it is it's not explicit. But it's way better even than these kind of expanders we've been talking about. So like here, epsilon 0 is 0.1, but for a random graph, the second smallest of the eigenvalue of the Laplacian is super close to 1. Like, it's amazingly large. Perhaps a better way to look at it in the context of a random deregular graph, let's say you have a random, let's say we have a random deregular graph. A good way to get such a graph, by the way, when n is even, is to pick d random matchings on the n vertices. It's very clear how to pick a random matching and then just superimpose them. This is a good way to get a random deregular graph. In a random deregular graph, let k, which is, let's call it G. Let k be 1 over d times the adjacency matrix A, as usual. So this, as I mentioned before, has eigenvalues 1. That's the trivial eigenvalue. Kappa 0. And then the next eigenvalue is kappa 1. The next one is kappa 2, down to kappa n minus 1. And to be a good expander, we want this kappa 1 to be far from 1, bounded away from 1. And it turns out, from this point of view, in a random deregular graph, not only is it kappa 1 bounded away from 1, it's super close to 0. And in fact, all the eigenvalues other than kappa 0 are super close to 0. And this is a theorem, a very famous and difficult theorem due to Friedman from 2000 maybe. It's famously like a 100-page paper, although it's been recently simplified to, 20 or 30 pages. But the theorem is that in a random deregular graph, all of these eigenvalues, kappa 1 through kappa n minus 1 in magnitude, are at most basically 2 times root d minus 1 over d. Plus little o of 1. That says n goes to infinity. With high probability. With probability, also 1 minus little o of 1. So Friedman's theorem says with high probability, you pick a random deregular graph G, and you look at this eigenvalues of its transition matrix, you're hoping that they're all, other than the trivial one, they're all bounded away from 1. In fact, they're all super close to 0. So this is the exact magic number, but in your head you can just think of this as asymptotic to 2 over root d. Okay, so if you make d like a big number, this is really close to 0, a big constant. Okay, and that's kind of awesome. And what we'd like to do is get explicit graphs that are close to this. And in fact, for some values of d, you can get this bang on. And this is called Ramanujan graphs. Okay, so what is a Ramanujan graph? It was fancifully named by Lubotsky, Phillips, and Sarnak in '88 when they constructed these graphs that are explicit expanders. Basically, they're explicit deregular expanders that have exactly this eigenvalue property. And they're actually constructed independently at the same time by Margulis, also in '88. And it's said that they're also implicitly constructed in the late 60s by Ihara. And as I said, what are they? They're deregular graphs G, and they have all of these kappa i's at most, this exact magic number, 2 root d minus 1 over d, literally exactly, with no plus little o of 1. So these are actually kind of amazing because they're, in some sense, like better than random graphs. Okay, by a little o of 1, but that's nice. But here's a little bit of a catch. The construction of these requires very heavy-duty number theory, like super hard, super deep. Well, the construction itself is actually not very complicated, okay? The vertex set is like all the 2x2 matrices with 1s in the diagonal and the other 0 down here and some number mod p in the other entry. And the edges are not hard to say what they are, but the analysis that proves that they're expander graphs and they have this expansion property is like super, super duper hard. It uses some deep number theoretic results of Pedersen, which are generalizations of some results by Ramanujan. So that's why they were called Ramanujan graphs. And there is another number theory catch, which is that they only showed them when you need that d minus 1 is a prime, which is congruent to 1 mod 4. Okay, so you don't get them for every value of d, but you get them for like a bunch of values of d, whenever d minus 1 is a prime. And actually, this was subsequently improved by Morgenstern in like 94 or something, to the case where any case when there's a finite field of size d minus 1, so d minus 1 being a prime power. So that's great. And these are also, they're definitely explicit. I think they're strongly explicit too, or maybe there's like some tiny caveat, but let me just say basically they're also strongly explicit. And that's great too. So these are wonderful graphs. Again, they're, let's say, strongly explicit, basically explicit. For any d minus 1 that's a prime power, you just write them down, and writing down the graph is not hard. The proof that they're great expanders, spectral expanders, is super hard, but they're actually like optimal spectral expanders. It's actually known that you cannot get anything better than this magic number, 2 root d minus 1 over d, basically 2 over root d. And that's, it's really close to 0. So it's like the epsilon 0 in the definition of spectral expander is really close to 1. It's like 1 minus 2 over root d. Yeah, so these are great as well. Another thing that is nice about them, there's a corollary of their number theoretic construction. Well, this corollary also takes work, but I like to mention it because it's like a super cute, explicit construction of an expander graph that results after you work through all the number theory in their paper. It's this. Consider the graph where you let v be the integers mod p, where p is a prime. And now, what are the edges? Well, you connect a vertex or a number a to a plus 1 and a minus 1, and one other thing, but so far a plus 1 and a minus 1 like makes just a ring, a cycle. And the last thing you connect a to is 1 over a, mod p. Okay, and the pedants will ask, what about if a is 0? Well, you treat 1 over 0 as 0. So you can just like put a self loop on 0. Okay, and so this gives you like chords. 1 over a is, if you do it twice, you get back to a. So this makes an undirected graph, and it gives you some chords, and they're pretty pseudo-random as it turns out. And indeed, this is enough to give you a 3-regular explicit expander. Okay, so the theorem is that this is like a n comma 3, well, I suppose I should say p comma 3 comma epsilon 0 spectral expander. And the epsilon 0 is really not great. I think it's, I don't know, like 1 over 100 or something. But hey, it's a positive constant. Okay, remember that means that all the eigenvalues, the second smallest eigenvalue of the Laplacian of this graph is at least 1 over 100, or the second largest eigenvalue of k equals 1/3 a is at most 99 over 100. Okay, so that's all I wanted to say about Ramanujan type expanders. And the last family of expanders I want to talk about is what might be called zigzag-esque expander graphs. Okay, so these kinds of expander graphs were developed by Reingold, Vedon, and Wigderson a little while ago. And what's cool about them is they're like an explicit iterative construction of larger and larger expander graphs, which is nice. And the analysis is pretty combinatorial, so you don't need any of the crazy hard number theory of the Ramanujan graphs, and you don't need the somewhat long and painful, well, it's not so bad, but kind of long and mysterious linear algebra-based proof of the Gabriel-Galil expander graphs. And one more key aspect of this zigzag style expander graphs is actually these are the only known way to get those like really good bipartite expander graphs that we use in the applications. Well, we only really needed it for the coding application. If you remember way back when we talked about these bipartite expanders, we used the fact that the expansion from the left side to the right side was at least 0.8 times the maximum possible thing. Like every set S here expanded to a set of vertices of size at least 0.8 times d times cardinality of S. And getting that 0.8 is pretty hard. And this zigzag-based method is the only current known way to achieve it. So that's another good thing about the zigzag-based method. Now, I'm not going to tell you exactly what is this like zigzag method for constructing expander graphs, because subsequently to its appearing, people realized there's like slightly less complicated ways you could get similar iterative construction of expander graphs. Maybe again, not with these ability to construct these great bipartite expanders, but like sort of easier to analyze. And one method uses what's called the replacement product for graphs. And another method, which was recently developed by Dan Spielman in his course lecture notes, uses some kind of like a line graph product method. And probably one of these will be on the homework. I won't have time to prove everything. But these are sort of like slightly simpler than the zigzag product-based method of constructing expander graphs. So let me briefly sketch for you the idea behind the replacement product construction. And this replacement product of graphs is a way to take two graphs and put them together to make a bigger graph. And it originally was analyzed in a paper prior to this exact stuff by Jaramson, Tetely, and Vigoda. And, well, let me just quickly say, here's the idea, which perhaps will be explored on homework. Let G be a, well, an n, comma, capital D, comma, epsilon sub G spectral expander. And let H be capital D, little d, epsilon sub H spectral expander. Okay, and the funny thing here is the number of vertices of H is equal to the degree of G. So think of G as like a big graph, and think of H as like a little graph. And they have this compatibility condition that the number of vertices of H is equal to the degree of G. And there's this thing called replacement product. So it's like R in a circle that takes G and H and makes like a new, even bigger graph. This is a G replacement product H. And it's going to have some nice properties. So I can even tell you how this replacement product graph works. Even though I said G was a big graph, let's try this graph for G. This is an example here. Okay, this is not even a regular graph, but okay, don't worry about it so much. So this is a 3 regular graph. So you would need to, that's capital D equals 3. So to replacement product it with H, you would need a little 3 regular graph, maybe a triangle. That's H. And how does the replacement product work? Basically, you put a copy of H at every vertex of G. So let's do that. And then you put edges between these copies in the way that G had edges. So we need some like edges here and some edges here and some edges here and here and here, and maybe also some self loops. And you know, every vertex of G has degree 3. And now, you know, the associated kind of cloud of vertices has 3 vertices. So you can actually associate each vertex here with one of the outgoing edges. And so like every vertex in one of these clouds has like one outgoing edge. Okay, and so every vertex gets like one outgoing edge. Okay, hopefully that was kind of clear. And in fact, to make it simple, I lied. It has one outgoing edge. You know, each of these in H, the degree is little d. So in each one of these copies of H, every vertex has d sort of internal edge, internal neighbors. And instead of having each vertex have one external neighbor, you make it have d parallel external neighbors. D parallel edges as its external neighbors. So you actually just like make, you know, 3 copies of each of these edges. And the reason to do that is so that when you take now finally a random walk in this big graph, every vertex has like little d internal edges and little d like external crossing edges. Okay, and so that's set up so that when you take a random walk, at every step you have a half chance of doing an internal step and a half chance of doing an external step. Okay, and okay, when you do this construction, what are the properties of the new graph, G replacement product H? Well, it has d times n vertices. Because, well, we have G had n vertices and H had capital D vertices. And its new degree is 2 times little d. That's because I said, remember, you know, little h has d is little d regular, but we also, for each vertex in it, have d like external edges. So every vertex has d plus d edges that it touches. And the theorem, that's basically in this Jaramson, Tetely, Vigoda paper, is that it also has pretty good spectral expansion. its spectral expansion is epsilon h times epsilon g over 16. Okay, so if epsilon h and epsilon g are both like, constants, you multiply them together, you still get like a positive constant over 16. And, the idea is that, G is expander, so it's kind of like well-connected, and H is also an expander, so it's kind of well-connected. Then you put them together in this way, and, it should also be pretty well connected. So this is a way of taking two smaller graphs. You think of G as like pretty big, H is like a constant size, and making like, a constantly bigger graph. So what happened here? The number of vertices went up. The idea is we're going to start, with some expander G, and we'll do this replacement product with H and try to get a bigger expander. So the number of vertices went up. That's good. It allows us to make bigger graphs. And the degree actually went down. If you think about G's degree was D, and now it went down to 2 times little d. So that's good. We kept the degree nice and small. The only trouble is that this eigenvalue went down. I mean, let's say if you think of your big graph G as the main graph, it used to be epsilon G, and now you multiplied it by epsilon H over 16. So you kind of shrunk it, and that's bad. But it's not so bad. Okay, we kept the degree small. We made a bigger graph. Okay, the spectrum went down. Let's do a different move to make the this eigenvalue bound go back up. And one thing you can do is, if you have a graph G, another move you can do is square it. So the squaring of a graph has the same vertex set. And you put an edge between U and V if there's a length 2 path from U to V in G. Actually, this is not totally accurate. What you should do is put, if there are L different length 2 paths from U to V, then you should put L parallel edges from U to V. Another way to put it is simply that the adjacency matrix gets squared. That's exactly what's going on here. And what happens when you do this? Well, the number of vertices stays the same. The degree goes from d to d squared, because that's how many length 2 paths you have. And, well, it's not hard to show that the eigenvalues of a squared are the squares of the eigenvalues of a. And that's also true for the transition matrix K. The eigenvalues of K squared are the squares of the eigenvalues of K. So every, kappa I just goes to kappa I squared. Okay, so if these kappa i's were all at most 1 minus epsilon in absolute value, then now they're all at most 1 minus epsilon squared in absolute value. So the gap went from, the so-called gap from 1 went from epsilon to, well, around 2 epsilon. Okay, maybe 2 epsilon minus epsilon squared, but never mind about that. Basically 2 epsilon. So the point is this made the eigenvalue parameter, this eigenvalue gap, go up. Okay, so this gap went up by a factor of 2. That's great. The number of vertices stayed the same. That's fine. And the degree went up. And that's kind of bad. But we can now put these two moves together, right? Because the replacement product makes the number of vertices get bigger. That's good. And it brings degrees down. So if you make degrees go up, then you can bring them back down with the replacement product. And the replacement product makes the eigenvalue bound go down, but squaring makes it go back up. So that's good, and you can kind of iteratively interleave these and get good results. Actually, more generally, what you can do is look at the teeth power of G, where t is an integer parameter. This is the graph whose adjacency matrix is a to the power of t, or you put L edges between U and V if there are L paths of length t from U to V. And in general, this has n vertices if the previous one had n vertices, and the degree goes from d to d to the power of t, and the eigenvalue gap epsilon basically goes up to around t times epsilon. Okay, that's ignoring these like lower order terms. Okay, so right, so you can now iterate this, as I said. So how does this iteration work? I'm just sketching things here, but perhaps the full details will be on the homework. Let's say if H, so H is this like small expander graph that you're gonna start with at the beginning and keep using over and over again as your replacement product friend, and G is like a graph that's getting bigger and bigger and bigger. So let's say H is a graph that has little d equals 4, okay, 4 regular graph, and let's say its number of vertices is 8 to the power of t, and its second smallest eigenvalue of its Laplacian, lambda 1, is at least, I don't know, like 16 over t or something. Okay, what I claim is that such a graph H exists. So just buy that claim for now. So what happens? So now if we interleave, we start with a graph, well, we can start with a graph G, and now we interleave the replacement product and this power of t operation. And what happens? So we replacement product, and the degree becomes 2 times little d, which is 8. And let's see. Right, let's work this out. Okay, let's go back to our replacement product here. Good. So this capital D, which is the number of vertices of H, was like 8 to the power of t. So when we do this replacement product, the number of vertices goes up by this constant factor 8 to the t, and the degree is 2d, and the eigenvalue bound goes down by epsilon h over 18, and this is like the epsilon h over, what did I say? 16. This is epsilon h. So this goes up by, it goes down by this over 16, which is about, the eigenvalue gap goes down by around 1 over t. Okay, but then when we power of t, the eigenvalue, power of t, the eigenvalue gap, basically goes back up by t. So basically the eigenvalue gap stays constant when you do these two operations. And the number of vertices is getting larger and larger by a factor of 8 to the t at each step. Okay, and the point is that, right, since the degree of the graph at each step is 8, when you raise it to the power of t in this step, the degree goes to 8 to the t, which is the number of vertices in H. Okay, so I got a little bit muddled there, but I think it all matches up. And then when you, replacement product, this goes back down to 2 times little d, which is 8. Okay, so the degree goes from 8 to the t, back down to the 8, and so forth. And the eigenvalue gap goes up by a factor of, goes down by a factor of 1 over t, but it goes back up by a factor of t, and so forth and so on. Okay, and this is great. It makes bigger and bigger graphs, constant degree 8. Eigenvalue is like some absolute constant. And actually, really all you need to make this work is like a starting graph H. So you just need like a starting graph H, which has these properties for some t. With these properties for some t, the required properties for some t, and You just have to argue that that graph exists, because then, an algorithm can find it in constant time. And indeed, such a graph exists, an H exists. It can be shown with T being, I don't know, like 30 or something. I somehow convinced myself of that, like a random graph will have these properties. Okay, so actually this last step is makes it not so practical that you have to like brute force search for this, but actually there are other ways. You can take like a little mini expander using one of the other constructions, like a Ramanujan graph or something, just to assure yourself that this finite graph exists, and then you can use it in this iterative process to make bigger and bigger expander graphs. Okay, so this is basically the idea of the zigzag product. This is the replacement graph version. And as I mentioned, one great utility of this is it's the only known way to make some of these most sophisticated bipartite expanders with really great expansion. So those are 3-ish different ways you can get explicit expander graphs for your many applications: coding theory, derandomization, and whatnot.